So I have some points here, and what I want to do is write the Lagrange interpolating polynomial for this set of points. And I've got the formula for the nth kind of sub-polynomial here. And I want to walk through how to use it. So it really isn't hard per se. It's just that there's a lot going on, a lot of numbers and factors floating around, and it can just kind of get a little messy. So the first polynomial, I'm going to build off of that first point. And initially, I'm going to ignore that point, right? This is where we're going to end up. Let me put the final result here. And we can talk about where it comes from. So I'm going to ignore that initial point for a minute. And to make the numerator, each of the factors is going to be x minus the x coordinate of one of the other points. So I've got x minus minus 1, x minus 2, and x minus minus 3. Now to get the denominator, all right, that's what I'm going to go back, and I am going to use that point. I'm going to take the x coordinate of that point, that's the negative 2, and I'm going to replace all three x's in the numerator expression with negative 2. And that gives me what goes in the denominator. All right, now I've got a little simplifying to do, canceling some negatives up on top. The denominator simplifies just to a number, and that's going to be L4, 1. All right, so this is the first of the 3 polynomials that we're going to end up needing. Okay, excuse me, the 4 polynomials that we're going to end up needing. So to do the second one, I'm going to do the same thing. This time I'm kind of politely ignoring this coordinate. So I've got x minus minus 2, x minus 2, and x minus minus 3. Those are my factors in the numerator. Then I'm going to take the x's in the numerator expression. I'm going to replace them with negative 1, and I get what's in the denominator. Again, we do a little simplifying. We're just arithmetic, turn the denominator into a number, canceling some negatives up in the numerator. Okay, I'm going to do the same thing with the others. I'm not going to make you walk through. I'm not going to expect you to sit through watching me do this for all 4. I encourage you to kind of pause the presentation and see if you can't work out those remaining 2. Right? If you do, you should end up with this and this. Okay, so how can we take those four L polynomials and turn them into the final Lagrange polynomial? Well, to do that, I'm going to start with my final result, right? And we'll talk through where the pieces come from. This is the L1 polynomial. This is the L2. This is the L3. And this is the L4. And the numbers, negative 6, 10, negative 34, and negative 26, those are the corresponding y coordinates. Right? So the negative 6 goes here. The negative 10 goes here. Yeah, you notice that's positive 10. That L2 polynomial had a minus sign out in front, so I went ahead and simplified some negatives just on the fly as I was copying them in here. Negative 34 goes down here. And finally, whoops, not negative 3. It's the y coordinate that we need. That's 26. And there was a minus sign in front of that L4, which is where that minus comes from. Okay. From here, this is the nasty, messy part. You have to multiply all those things out. If you're lucky, you're comfortable with getting a decimal answer. And you can just convert all of those weird fractions, the 34, 60ths, and so on, to decimal values. If you do that, and you're very careful and very patient, you'll end up with this expression, this polynomial, as the final Lagrange interpolating polynomial for this set of points. So I've got our final result here, and before I move on, I just want to make a couple observations about it. First, as I was saying on the last screen, these polynomials are great, but coming up with them can get messy. It's helpful if you have some kind of symbolic processor that will, like Mathematica or Wolfram Alpha, some that will multiply out that otherwise very messy polynomial for you. And notice that the degree of the polynomial here. We have 4 points, and to determine each of those subpolynomials, I goes from 1 to n, but it skips that one value where I equals k. So we end up having n minus 1 factors in the numerator, which suggests that we're going to get a polynomial of degree n minus 1. And first, that is what happened here, where we had 4 points, so we ended up with a third degree polynomial. And it's also kind of consistent with what you've seen in previous classes. The general rule is a nth degree polynomial requires a minimum of n plus 1 points to uniquely determine it. And again, that's what we're seeing here. I do want to point out that it's not a requirement that it be a third degree polynomial or an n plus 1 degree polynomial. That's just the maximum possible result. And we'll see more about that in the next example. Speaking of which, I've got a link to that example down here. I've also got a link back to the lecture where we kind of came up with this formula, if you'd like to see the full context. And of course, if you like this presentation, please don't forget to click on the like button down there as well.